Okay, let's just wait for a few minutes so that others can join, and then we will start the session. So today's session is based on the specific heat and how scientific community actually evolves with it to get the right estimation of the specific heat. So all the lectures are based on that, and the problem solving and problems are also based on that. And the later part is about the real and ideal gases, that their differences. So we'll begin shortly so that others could join. Okay, so let's start today's session. Seems there are very few attendants in today's class. Anyway, we'll start the session. Otherwise, it will be too late to cover all these things.
Good evening, sir.
Good evening. Okay, so um, as you know, I am Dibyendu. I work in software and activator lab. So I am one of the TAs for the problem solving sessions for the course thermal physics. Course ID as NOC 24 page 17, and the instructor of the course is Professor Debamalya Banerjee, who is from IIT Kanpur. So today's problem solving sessions will be based on week number 5, and and problems will be based on those things. So without further ado, let's start. So the first question says, calculate the value of Einstein's frequency for a solid for which the Einstein's characteristic temperature is 300 Kelvin. So, firstly, do you know how the Einstein's frequency and how it comes and all these things? Have you followed the lectures? Or I should uh, recap few things about Einstein's specific. Okay, since there is no response, looks like I have to do these things. Okay, so just for this thing, I will solve the problem first. This problem, then I will add the thing. Okay, so first the Einstein frequency actually it is denoted as, if I just can write it, which is denoted as, you can, so I in Einstein specific heat or specific heat for solid theory, he assumed that all the molecules which are at the lattice points, they vibrate with a single frequency, right? Now for this thing, let's say the uh, vibrational frequency of Einstein solid, let's say this is this one, so, or you can write it as omega naught, whatever it is. So that actually comes as, this one is kBt divided by h cross, the Planck constant. Okay, so I will derive these things. I think it will be helpful for you if you derive alongside me, and if you follow the derivations, then some things will be clear. So I will just solve it, and then I will start the proof shortly. Okay. Now, what has been said is temperature T has been given as 300 Kelvin, right? Okay. So you can write. So let me write it in another notation. So here this will be Einstein temperature. So this is theta E. So this will be Kb theta E by h cross. Let me write over here that theta E temperature. What is h cross? Anyone knows?
1.05 into 10 to the power of minus 34, sir.
Yeah. So is this Planck's constant? So this will be h, not h cross. Okay. So h cross is h by 2 pi, right? Let me see. So let me see the actual value of the Planck's constant. Okay. Just a minute. Okay. This is 6.6 10 to the power minus 34 joule second. Okay. Let me write it here. 6.6 10 to the power minus 34 joule second. Okay. Now put this value into these equations. That will be Kb. What is the value of Kb? Kb is Boltzmann constant, 1.38 10 to the power minus 23. What is theta E? Is 300 Kelvin. You put it here. And Planck's constant 6.6 into 10 to the power minus 34. So this will be second inverse. And if you do the
Sir,
calculations,
H cross means 1.05 then, sir.
yeah,
Are you right it 6? H Planck's constant only 6.6,
yeah,
sir.
this is Planck's constant. That's
But
why yeah. This is,
here are you write it H cross?
no. You just missed the point. So this will be h. I just mistakenly write it here. So
Okay, sir. Thank you.
you missed the point. So this will be h. Okay, let me write it freshly. Otherwise, there will be more confusion. This is h. Okay, Planck's constant. I write it here. So H cross is reduced Planck's constant, then that will be 2 by 2 pi. Okay, so he's rightly mentioned it. Okay, so please do the calculations and tell me what is the value is coming up.
Option C.
Option C means 6.27 10 to the power 12.
Yeah.
Okay, let me check with my calculations. Uh, yeah, absolutely correct. Absolutely correct. This is coming out to be 6.27 10 to the power. Thank you. Second inverse, which comes to be 6.27 10 to the power 12 hertz. Okay. So option C, as Renuka Devi mentioned, option C is correct. So this is correct. But I can stop here, but I want to actually give you some flavor of how specific heat and this kind of specific heat of solids and their sort of evolutions, how theoretically they were calculated, and how quantum mechanics, with the advent of quantum mechanics, theory could easily or actually rightly predict uh, the values at low temperature regime and high temperature regime. So I would like to do those things. So be with me, and I think it will help you. Okay. So just a minute. I will add some page here. Okay. Yeah. So someone wants to join. Let me. Yes. Yes. Okay. So all of you know what Dulong-Petit law is? Who knows the Dulong-Petit law? Looks like no one responds.
Find out the specific heat capacity, sir.
Yeah, yeah, yeah.
Find out specific heat capacity of your solids.
Solid. And what was that value?
3.
3
3
or
R.
3R. Yes, yes. You're absolutely right. So what are the what are what are those assumptions in calculating or theorize Dulong-Petit law? Do you know those things?
I think 2.96 only. Carbon and little bit theory is there. That is I'm forgetting.
No, no, I'm not talking about the I'm talking about the carbon and all this. I'm talking about that they did some experiments and then they tried to give some theory to stand,
I
explain.
think high temperature, Dulong-Petit law and Einstein theory, everything also 3R. At
Yes,
low temperature, directly proportional to T cube.
yeah. So
Yeah.
yeah, there are different things. So not only T cube, there is AT plus BT cube, and this kind of thing happens. But I'm not going into that. I'm talking about the assumptions, the basic postulates that that those two scientists considered while calculating these things. So they
Some
assumed.
point is there, sir. Now I am not
Yeah, 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 yeah.
forgetting. One
But
second, you can tell me, sir.
yeah, but you are actually on right path. Thank you so much. So what they assumed, that they thought the solid as a arrangements in the lattice points of you know uh, some harmonic oscillator, not an oscillator, some molecules which is vibrating like some harmonic oscillator, and they are independent. And he considered that they are, since their degrees of freedom are 6, because if some molecules is there, so there will be 6 degrees of freedom, right? 3 rotational and 3 translational, and they are independent. So what they considered, they actually mixed. Okay, let me write it here. So they mixed Dulong-Petit law, as Renuka Devi rightly suggested. So they actually do, in 19th century they did those experiments in 3 kind of solids and their arrangements, and they found out to be CV is proportional to be 3R, and to be more specific as 3 in KB. When N is equal to NA, then R is actually nothing but RA in KB. Okay, so they actually did these things, 3R, 3 N KB. What they considered is, let me write it here, they considered Dulong-Petit. They first they considered equipartition theorem, equipartition of energy, and they considered 6 degrees of freedom of each molecules. Okay, so you can see here, right? So there are 6 degrees of freedom, 6 times each point will give you half kbt, but if you take the derivative, there will be only kb. So this is for each molecule, and there are n molecules. If you do the calculations, this is coming out to be 3 n kb. So this is the thing, but if you noticed here, there is no temperature dependence. Okay, so what they are saying from Dulong-Petit law, that specific or heat capacity at constant volume will be same for at low temperature and as well as at higher temperature. But when people are interested in studying different or more solids, they saw that at first of all that actually at lower temperature it is not matching, because that when temperature decreases to absolute temperature, which is T equal to 0, absolute 0 temperature, so there actually all these things freezes, all kind of thermal motions freezes, so heat capacity should be 0 there, right? But it is giving some constant value, so there are some discrepancies, and people were trying to do different things to get the actual prediction. Then after effort of a big chunk of scientists, at last Einstein came to rescue. At 1911, he gave a certain theory which actually that time was predicting this specific heat rightly. So we will just derive this thing. Okay, so what he first considered, he take 3 assumptions. Okay, so he first considered all molecules at the lattice points vibrates as harmonic oscillator. Okay, so the first thing he assumed that uh, all those things will be vibrating independently. And second thing, just yeah, second thing, that they are not interacting with each other. Okay, they are not So they are independent. Okay. And third thing, that they have a fixed characteristic frequency which we just calculated, right, which is omega naught or theta e, sorry, omega e, whatever you can call it. I will, for derivation I will consider omega naught. So they have fixed characteristic frequency with which all molecules vibrate. Okay. So there are flaws with these 3 points, and so what will be the degrees of freedom for each vibration? That will be 3, right? So 3 vibration, 3 degrees of freedom. Then so this is the thing. So first point, which is all molecules vibrating, so this is quite true for, for the advanced model, which is Debye. But there are few things which are, different. For option, for point B, which is not interacting, that is not also true, because in you can feel that, right? If you take a piece of metal and you strike it, you can see some, some kind of, sound coming out of it. So if there is these things are not interacting, then how can you strike at one end and you can hear the vibration other end? So that phonons, which is called the sound wave, these phonons actually moves along this lattice point through the lattice points. That's one thing. And also this fixed characteristic frequency is also not true. It has some range, but I'm not going into that thing because that will take more time, Debye theory, because it takes more quantum calculations. But I can calculate this thing for sure. That will be easier. Okay. Okay. So okay. So so what is in quantum? So he used quantum theory, quantum. Sorry, he doesn't. So let's prove it. So for using quantum mechanics, what is the energy of a single, this thing, single harmonic oscillator? So it has this kind of thing, n plus half h cross omega naught. So omega naught is the characteristic frequency. So you can omega naught and this omega e are same, mu e are same, but I'm for the writing convenience I'm using omega naught. Okay. So what will be the average energy then? Average energy E bar. So that will be, this will be, so average over all these things. So this is En. So this is En by kBt. So this is Boltzmann. We are considering Boltzmann distribution, and this is e to the power minus En by kBt. Okay. Now if you write, then how this is going to be changed is, so what is, let me put up now. So this is equal to n equal to 0 to infinity. En is n plus half h cross omega naught. Then exponential of minus h cross omega naught by kBt. But there is also be n plus half. There is also be n plus half. Now how can I write it in terms of different thing? Let's say I can write this term. So this can be taken out because this is constant. So h cross 0 to infinity n plus half e to the power plus. I'm not writing the limit every time because you know this will be 0 to infinity. Okay, so this is n plus half. Now you can see, if I take this quantity as x, this quantity as x, so that will be what will that will be. So let's say x is like this, x, sorry, let's say x equals to minus h cross omega naught by kbt, and if you substitute this term will become n equal to 0 n plus half to the power minus x times n plus half divided by to the power minus x, sorry, there will be no minus, n plus half. Okay, now if you see in the denominator, the e to the power x times n plus half, if you take that as y, and if you take the log of that and take the differentiation, so then what is the differentiation of log? First 1 by x, and I will do the multivariable differentiation step by step, and then first it will be, so let me write it in terms of, so let me consider y is equals to summation over n equal to 0 n plus, sorry, e to the power x times n plus half. Okay, so if that is that, then what will be, so what will be ddx of ln y? First will be y times dy dx. Any problem with this thing? Writing this ddx of ln y is equal to 1 by y times dy dx, right? Now what is dy dx then? If y is that, then if y is sum over 0 times half n, sorry, to the power x times n plus half, then dy dx will be n plus half times e to the power x n plus half. Any problem writing this thing? No problem, right? Now if you see this thing, then you can write the whole thing as y. What is y? Y was this thing. So this is n equals to 0 to infinity e to the power x times n plus half, and in the numerator, so in the numerator this n plus half times e to the power x n plus half will come, right? So this will like be n plus half e to the power x n plus half. So far we haven't used any quantum mechanics except to consider the energy of harmonic oscillator, which is quantized n plus half h plus omega naught. Okay. Now this is that. Then I can easily say the whole thing in let me here. Then this whole thing will be ddx of ln y, right? So this is actually written in this thing. Then we easily write E bar will be h cross omega naught times d dx of ln y, right? So we'll write that here. Just a minute, let me change to pen. So then E bar will be h cross omega naught d dx times ln y. Okay. Now there is interesting thing. Okay. The interesting thing is, if that is the thing, then I can easily write. What can I write? Y. This is y, right? So y can be written as first for what will be the first term for n equal to 0? This will be e to the power x by 2. E to the power x by 2. Second term e to the power 3x by 2. Third term e to the power 5x by 2, and so on. It will continue because this is infinite series. And if you take out e to the power x by 2 outside, then I can write in terms of 1 e to the power x plus e to the power 2x plus e to the power 3x and so on, right? So this is an infinite series, right? This is an infinite series, right? Runika Devi? Nana Sekar? What will be the value of this infinite series if you take the summation? What will be the value? Anyone? This is simple, right? An infinite series, if you are taking the sum. Okay, probably you guys forgot. Let me write it here. So this term will be 1 divided by 1 minus e to the power x, right? So then I can write it as e to the power x by 2 divided by 1 minus e to the power x, and if you take the log of this, then what will become? H cross omega naught d dx ln. So log of e to the power, lot of algebra is going on, so please keep track of all these things. So log of a by b is log a minus log b, so this will be h cross omega naught d dx log of first e to the power x by 2. So let me differentiate it. Minus log of 1 minus e to the power x. Okay, so it will become h cross omega naught. So ddx of this one will be e to the power x by 2. So e to the power x by 2 minus log of 1 minus e to the power x. And if you take the differentiation, so this will be h cross omega naught divided by half, sorry, ddx of x by 2 is half minus, so first thing log of this, so e to the power minus x and then here again e to the power x minus, after rearranging it becomes h cross omega naught half plus e to the power x divided by e to the power minus. Okay, so far it's good, right? Now average energy we have just calculated, we didn't calculate the specific heat up till now. Okay, so now we'll add one more slide. Now, so this is the last value that we got. Okay, so here we will write this. So E bar h cross omega naught divided by half plus e to the power x divided by 1 minus e to the power x. Okay, now what is specific heat? Specific heat Cv minus d epsilon dt, keeping V fixed. Okay, now in my case it has then become, what will be the total energy? Total energy, my total energy E will be in E bar, because average energy is that. Okay, just me. So this is this thing. So this will be Cv d dt by V. Now if you write that thing into these calculations, this will become 3 by 2 in h cross omega naught plus 3 in h cross omega naught to the power. Now we can multiply by e to the power minus x in two sides. It will become then e to the power minus x divided by e to the power minus x minus 1, right? Now what is x? X was, what was x? X was h cross omega naught by kbt minus, right? So if you substitute this here, it becomes 3 by 2 in h cross omega naught plus 3 in h cross omega naught e to the power h cross omega naught by kbt divided by e to the power h cross omega naught by kbt minus 1. Now you take the differentiation, right? Cv is equal to minus d dt. Okay. Now the first term, this first term will be 0, no problem with that. In the second term, for this thing, so let's take, we have to take the difference. Okay, so okay, so we calculate, so this will be not here. this term will also not be here because we have calculated e to the power minus x. So this will be 1, this will be e to the power minus x, minus this will be 1. So only term there is t is this one. So this is in the denominator. So this is 1 by x type kind of minus sign is there, minus of differentiation. So first this will be square, right? E to the power minus h cos omega naught by kbt minus 1. This is squared. This is there 3n h cross omega naught. Then this thing. So this will be h cross omega naught by kbt, sorry, kb times e to the power h cross omega naught by kbt, and for this thing 1 by t, so this will be minus 1 by t square. Okay, so if you take the whole thing, then it will become 3n kb. So there is kb here and kb there. So if you, so minus minus cancel out, so 3 in kb, I have kb times 1, so there will be one more kb. So h cross, there is 2 h cross omega naught. First one is, there is one, this one. So this will be h cross omega. One is 1 kb here, 1 kb here. So this is kb, and there is t square. So this is t whole square times e to the power minus h cross omega naught by kbt by e to the power h cross omega naught by kbt minus 1. Someone wants to join. Okay, so here that is the CV. Okay, now I have to but check this thing. So you got the Einstein, this thing Einstein frequency, right? So Einstein frequency then can be written in terms of here. So this is CV. Then CV will be, so theta E is, theta E, let me write, theta E is equal to h cross omega naught by kb. Okay, so h cross omega naught by kb as theta, because this can be written as this thing. This is Einstein temperature. Let me write it. Einstein temperature. Okay, so you can write then CV as 3n kb theta E by T whole square divided then times e to the power theta E by T e to the power theta E by T minus 1 whole square. So this is the actual form. Now let me add one more this thing. Now our main goal is to get the high temperature limit, because I have to see, right, that why Dulong-Petit law was valid at high temperature. So at high temperature, let me write here. So at high temperature, so when high temperature will be there, then T will be very very greater than theta E. So theta E by T, this ratio will be very very less than 1. So e to the power theta E by T can be written as 1 plus theta E by T. Then this expression will be changed, right? So let me write in this expression again. Then CV 3n kb theta e by t whole square e to the power theta e by t. So this thing will become, for this will be just like this, theta e kb plus theta e by t whole square. Okay, now theta e by t, how that will be? This will be 1 plus theta e by t, right? And this will be theta e by t, 1 plus theta e minus 1 square. So theta e t, this will cancels out, and only thing will be this one. So I can write actually this energy, actually that will be more uh, good thing to write, this average energy, that will be this thing too. So now you can see that here 3n kb plus 1 plus theta by t. So for very high temperature, for very high t, theta e by t very less than 1, then Cv tends to 3n kb. So we'll get back the Dulong-Petit's law. So this is a long calculations. Any questions so far, or should I proceed to the next thing, or I will actually repeat this thing in the, when the problem solving sessions will be over, all the problems will be discussed. So let me quickly actually summarize for 1 or 2 steps. So actually the question arises that what will be the difference between Dulong-Petit's law and the Einstein's law for specific heat. So first thing first, in Dulong-Petit's law, they considered as molecules with 6 degrees of freedom, and they actually equate with uh, uh, equipartition theorem, and they actually they gave this Cv is equal to 3R or 3n kb. But in Einstein, but at lower temperature or intermediate temperature region, there are some discrepancy. So Einstein came up with some theory where he assumed these 3 things mainly, when he considered that all molecules at the lattice point vibrates like harmonic oscillators, and they are not interacting with each other, they are independent, and they have, all those molecules have fixed characteristic frequency, which is omega naught or nu e, that is called Einstein frequency, with which all molecules vibrate. Now we have used only the quantized energy of harmonic oscillator, which is n plus half h plus omega. We have calculated the E average, the average energy per molecules, and after that average energy, we will get the total energy, which is E equals to number of molecules time average energy, and after that if we get the total energy, we will get the specific heat by using these thermodynamic relations minus dE dt, keeping V fixed, and we have get this complicated figure. But since we know that at higher temperature Dulong-Petit's law were valid, we have taken into account at higher temperature limit where T very less than, very greater than theta e, which is Einstein temperature. So their ratio will be very less than 1. So the exponential will be truncated in this way, and we have got that really at higher temperature Cv actually converges to 3n kb. Okay, so lots of talking. I will actually proceed to the next problem. So the next problem says, so now I am giving you all the formulas. Now I am expecting to participate or to give me the actual answers. The question says, Find the temperature at which the Einstein's frequency is 5 times 10 to the power 12 Hz. So what will be the formula? Can you do this? I'll wait for 2 minutes because I have written the formula. So you guys do this and then tell me the answer.
Sir, h power omega naught by kpt.
Yeah, you can use that. So you see, the way we have calculated, we have actually okay. So okay, sorry, my was off. So the way I have calculated, it doesn't take the whole quantum mechanics into account, because this oscillator, they actually do not follow Boltzmann distributions. It follows different distributions. But you can use the formula just like that h omega divided by kb. Same formula as the previous one, right? Hello? Hello?
Sir, tell me, sir.
Yeah, so we will use the same formula as the previous one in the question number 1. Only thing there
Sir,
was,
question number 1, given the temperature, are you calculate the frequency?
yeah, but just you have to role reverse this, right?
Yeah, here also kp by,
H,
sir, frequency kp theta e by h, sir.
H, sir, yes, yes. Here just,
Yeah, Einstein.
yeah.
Okay, sir.
So now we have to find out the theta e, right? And mu e is given.
E means the formula h bar omega naught by kpt, correct, sir?
That is also correct. That is also correct, but there is some,
Okay.
yeah, your point. So that is also, you can write it. Yeah. So there will be some prefactor changes only. No other problem will be there, right?
Okay, sir.
Yeah. So actually, since this is Einstein frequency, so we will use in. So what is the relation between angular frequency and frequency? So let me write it here. So in this case,
239 Kelvin.
239 Kelvin. I haven't calculated. Okay, 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 okay. Let me get back to you. Let me, others to join. So others to join means others to, tell me the answers. So here, this is this one. This is actually, this one is 2 pi omega naught. Okay. So in my calculation, I have used angular frequency omega naught. So omega naught and this nu e are related by this thing. So here by Einstein frequency, by saying Einstein frequency, the questioner actually given this frequency, right? Not omega naught. So actually I have in my calculation, this is h bar omega naught. That is actually similar. That value will give you the similar than this, right? Similar value of this, right? Is this clear? Is the point is clear?
Yes, sir.
Okay. Now, as Renuka rightly said that, so what is the, this one was there, this was h cross. So theta e, Einstein temperature theta e was h cross omega naught by kb, right? So we can write it's h nu e divided by kb. And what was the value of h? This is 6.6 times 10 to the power minus 34, and nu e is 5 times 10 to the power 12 Hz divided by kb, which is Boltzmann constant 1.38 10 to the power minus 23, right? So this is will be Kelvin, right? Now if you do the calculations, it is becoming, so for my case, 6.6 times 5 divided by 1.38, it's coming out to be 239.1. So 239, okay, 0.13 Kelvin. So Renuka, you are absolutely right. So the answer is option A. Okay. So same thing. So only in my calculation I have used angular frequency and this is frequency. There is some conversion factor. So whatever you use, you will get the same answer, right? So if you use omega naught, then you have to multiply with h bar or h cross. Okay. Whatever. So let me write this kb is Boltzmann's constant. Otherwise, and Einstein frequency. Let me write here also when I have written this. So omega naught is equal to 2 pi. Okay. Okay. So the next problem. Next problem says, if the Einstein temperature for a material is 75 Kelvin, compute the value of Cv at a temperature 50 Kelvin using Einstein's formula, given R is equal to this value. So can you do this thing? I have calculated the formula, right? So in my case, it's coming out to be 3 nkb, but if you for Avogadro number of particle, this will be 3r and this will be x. Let's say this is x or y, let's say y square e to the power y by e to the power y minus 1 whole square, right? I have used y also in the, let's say z, or let's say y. Here y is equal to theta e by t. Can you use this formula and do the solution? This will be the same formula, right? Same thing, right? So use it here and do the calculations. Okay, I'm waiting.
Sir, please once again tell me, sir.
Yeah,
3n kp and then
3n kb.
what is the remaining, sir? Remaining part?
Okay, okay. I'm just showing the formula. This formula in the what is underlined. Can you see it?
Sir, yes, sir.
You can see it, right?
Yes, sir.
Yeah. You have written the formula. I can okay, go back to that slide. Right.
Once again, you can explain, sir.
Yeah, got the answer, or should I give the answer? Hello, hello.
Sir, I am not get correct answer, sir.
Okay, okay, okay. But you have tried. That is good thing. Okay, so you know that formula was given, said for nothing is correct answer. If your formula it's this thing and you are inputting those things correctly, whatever answer you will get, that is the correct answer. For Einstein's specific it, this is CV becomes 3r y square to the power y divided by to the power y minus 1 is just y or minus y. Yeah, y to the power y square, where y is theta e by t. What is theta e? Theta e is Einstein temperature is 75. This is 50. So this is 1.5. And so this is, if you put it here, CV 3r, r is 8.3, y is 1.5 squared e to the power 1.5 divided by e to the power 1.5 minus 1 square. Okay, let me put it in my calculator. So 3 times 8.314 times 1 square times e, right? What is e? Times e 1.5 divided by e 1.5 minus 1.
Sir, option B,
Just a minute, I'm calculating. Okay.
20 points. Okay, okay.
Yeah, option B is coming 20.7479, something like this. Okay. So for my calculations, it's coming out to be 20 point. So why we're not able to got this thing? Because you know this, right? This is Joule, mole inverse, Kelvin inverse. So this is the value, and nearest value is this one. So this is the correct answer. So this is just from the formula we have derived few minutes before. I think everyone should participate in these calculations, because I have just discussed this. If you haven't gone through the lectures, then also you can just since you are here, you have the formula and you have to put it here, right? Any problem with this thing?
No, sir. You
Okay,
can move on next.
okay. So the next problem says, so according to Einstein's theory of solids, which of the following is true? And I have just discussed it. Okay, so I think uh, I should expect everyone's answer. Option A says atoms do not vibrate at all. Option B, all atoms vibrate with a single frequency. Option C, all atoms vibrate in a range of frequencies. Option D, each atom vibrates with a particular frequency. Tell me the answer. I have just discussed it. I have proved the Einstein specific heat theory and derived the calculations. So tell me, which option is correct?
Sir, option D.
Option D or B?
Same frequency means single frequency. All atoms vibrate with same frequency, sir.
Which one? Which one option then? B or D?
That's only confusion, sir.
No, no, no.
I think single
Okay,
frequency
so
means
so
same.
so so the my point was that each atoms or each the molecules who are there in the lattice point, they are vibrating in a single frequency. So option B is correct, but option D is saying each atom vibrate with a particular frequency. Mean frequency associated with each a single atom is specific. That is not same for every atom, right? So that's why option D is not correct.
Okay, sir.
So option C is also not correct because all atoms vibrate in a range of frequency that was not considered in Einstein's theory of specific heat, right? So that was considered in Debaye's theory, and atoms do not vibrate at all. That is completely wrong. So in that scenario, so this is so in Einstein theory of solids, all atoms at every single lattice points vibrate with single frequency. Okay. Okay. So next problem, the specific heat value for a solid at very low temperature is accurately given by option A, Dulong and Petit's law, option B, Einstein's formula, option C, Debaye's equation, option D, all of the above. Which one is correct? If you have gone through the lectures, then you will, this is just cakewalk, right?
Sir, Debye equation at low temperature, Debye equation, sir.
Exactly. Why is so?
It's only proportional to T cube. D cube law. CV proportional to D cube law.
Yes, but the in Einstein's,
But
yeah,
that two things, Dulong-Petit law, Einstein law, all everything's also rectify the problems. I think assumption. Here,
yes,
Debye theory give the correct way.
yes. So there are some shortcomings in, so Dulong-Petit's law. There are many shortcomings. Then the new version in the Einstein's formula, there are some all most of the things were sorted, but some few assumptions like all the particles, all the atoms in the at lattice points, they are vibrating with single frequency. That is also not correct. That actually that was been corrected by Debye by considering a frequency band, and also the these atoms are not interacting. That is also not correct, right? They were some phonons, as I had told you, that if you hit some rod or metal thing, you will see the clinking sound. Or if you hit one side of a pan, frying pan, then other side will also be heated, right? So that's why device equation, Renuka, you are absolutely correct. So this is device equation, this is just theory. So let me go back, proceed to the next problem. Then tell me this thing. For a solid, the Debye temperature is theta d is 500 Kelvin. Calculate its specific heat at a temperature 75 Kelvin, assuming low temperature behavior. Given R, the value is given. So tell me, do you know the formula or should I write it? Okay, I will write it, then please calculate it. So d by temperature is given, right? This is theta d is 500 Kelvin, and Cv, this is 4 pi to the power 4 divided by 5 times 3r times T by theta d. So as Renuka was saying that d by is T cube law, here you can see that specific heat or heat capacity is varying as T cube, right? So everything is given, please calculate it and tell me the answer. I want a different name this time. So Renuka is doing fine, and other than Renuka, I want to get the answer. And Renuka, you also do it and tell me the answer. Okay. Anyone else? So Renuka has got one answer. Anyone else? I'll wait for one more minute. Okay. So let's see, is Renuka's option correct or not? Okay. So then CV 4 pi to the power 4 divided by 5 times 3 8.314 times T is 75 divided by 500 cube that is Kelvin inverse, right? Joule mole inverse. So for my answer, it's coming 6.5.
C option, sir. I am not cube the value. Sorry, sir.
Okay,
Sorry
okay,
for mistake.
okay. Yes. So this is Joule mole inverse, Kelvin inverse. So this is the correct option. Okay. So option C is the correct one. Okay. So now, so this one. For a certain metal, the velocity of longitudinal waves is half the velocity of transverse wave. What is the Debye frequency if the number of atoms per meter cube is 10 to the power 29 and the velocity of the transverse wave is 3 km per second? I expect that you guys do not know the formula, so I will write it here and then you guys solve it, because you are not all. So omega, assume Debye frequency is, let's say, mu d. Okay. Now longitudinal velocity, let me write in terms of CL, and transverse velocity, this is CT. Okay, CT, and it has been written that CT is equal to 3 km per second, which comes to be 3000 meter per second, and CL, longitudinal waves, is half of CT, right? Half the velocity of transverse, so CT by 2. And so this formula omega d is equals to 9 n by v divided by 4 pi times 1 by CL cube plus 2 by CT cube. Okay, so do the calculations and tell me. It will take a bit time to do the calculation. And n by b is also given, right? N by b is 10 to the power 29. N by v equal to 10 to the power 29. So tell me the answer. There will be 1 by 3 once. There will be 1 by 3. Sorry, there will be 1 by 3 of this thing. Whole thing there will be. Okay, so let me do the. It's too difficult. Okay, so now if we put it here, all the values, let's say this is 9, this is 10 to the power 29, this is 4 pi, this is 1 by CL cube, so CL is CT by 2, so CT by 2 cube, 1 by plus 2 by CT cube, 1 by 3. So if you take CT cube common, 1 by CT cube, then it will become here, right? So 9 into 10 to the power 29 divided by 4 pi, this is 8, this is 8, so 8 plus 2 whole is 1 by 3, and this is CT. And if you do these calculations, for my case, it's coming out to be 9 times 10 to the power 29 divided by 4 t times y. Answer into, yeah. So if you do these calculations, so my calculation is coming out to be, I maybe did some mistakes, but whatever, 5.87 10 to the 12 hertz. So you guys also do the same calculations and see whether these things are matching or not. So this will come around these things. What I'm trying to say is you can get some idea, right, from this thing. Okay, so another solid, just
Sir, once again you show me previous answer,
yeah,
sir.
yeah. Arey, just a minute. Yeah, can you see it now?
Yes, sir.
Yeah. So there can be some numerical thing, but what the important thing is this one. So this
Sir, why we can multiply with again CT here?
again, no, we will get city right from here in this, from this portion. So
Okay, sir.
this is 9 times 10 to the power 29.
Okay, that's everything. Denominator.
Then city cube is in the denominator of this, on this thing.
Sir,
Then this will be
CT value is,
300,
I
3000.
think, 3000.
Yes, yes,
CT by 2 means 1500, whole cube means directly correct, sir.
yes.
That CT cube 3000 also correct. 2 dividing that answer means no 10. And why you again multiple with CT?
No. This is coming out to be city, right? From this step to this step. So this is city cube, right?
Yeah.
So if you take city cube outside from this bracket, then here it will be 1 by city cube.
Okay, sir.
From up till this point, this is clear. 1 by city cube. Hello.
Yeah, yeah. Yeah, sir.
Now there is cube root, right? Now if this is 1 by city cube and this is 1 by 3, then there will be 1 by ct, but there is also, that is in the denominator, so that will come in the numerator, right? Is the point taken or not? Hello. So here if you take,
Okay, sir.
this is
Okay, okay.
this is 1 by ct cube, and if you bring this here,
Okay, now clear, sir.
this is ct cube, then this will be ct, right? Okay, so now tell me this answer. At very high temperature, the temperature dependence of the specific heat of solids is given by this. Now this, please tell me the answer. After doing all these calculations and all these things, please tell me what will be this thing. Renuka, what will be this value? Or Perumal, Murugan?
Solids.
Yeah.
Solids means option C, correct, sir?
Why option C?
Sorry, CV is constant.
Hello.
Sir, CV is constant.
Yes.
At
Why
high
so?
temperature, 3 theory also constant. CV is equal to 3R.
Yes.
But low temperature only value will be changed.
Yes. Yes. Absolutely
Yeah.
correct. So using Dulong-Petit's law, using if you use Einstein's theory, or if you use uh, device specific heat theory. In every sense, at higher temperature, that will give you 3R, right? 3 nkb or 3R, right? So that's why there was no problem in calculating Dulong-Petit law. So this will be correct. So at high T, CV becomes 3R or 3 nkb, whatever I want to write. Okay. Now this problem: 1 mole of a gas.
Sir, please, 1 second, sir.
Okay, okay,
Getting noted. 1 second.
yeah. You
Okay, sir, you can move.
you will get all these lecture slides in the PDF format. Are you accessing those things?
Yeah, side by side, I will note it, sir. That's only problem.
That's very good. That's very good. This is actually recommended every time. Whenever you
Okay, sir.
attend some lectures, this is very good. Anyway,
Okay, sir, you can move.
yeah. So this problem: 1 mole of a gas occupies a volume of 0.6 liters at 27 degrees centigrade. Calculate the ratio of pressure exerted if it behaves as an ideal gas and as a van der Waals gas. Given the van der Waals parameters are given, A and B values are given. So this is quite simple. Van der Waals gas and all these things you have studied class 2, but I will give you some formulae to calculate. So what is, I will denote Pi as ideal pressure if it is ideal gas. This is Pi, and pressure if it is van der Waals. Let's say VPV. Now for ideal gas, what is Pi? There is 1 mole, so no problem with that. nRT by V, right? So N is 1, R is given, RT by V is 0.6. So if you write this thing, so this will be Newton per meter square. R is 8.31, temperature is 300, and this is 0.6. So this will be Pi. Now what is PV? PV. PV is RT my V minus B minus A by V square. This is for 1 mole, right? Now put the calculation value here, R, and please tell me the answer. So in the meanwhile, I will calculate this value. 8.31 times 300 divided by 0.6. So this is, so it's in, this is deciliter, so this will be 10 to the power minus 3. So this becomes 4.155 to the power 6. Okay. Calculate this thing. I will do it side by side. Then 8.31 times 300 divided by P, which is 0.6 into 10 to the power minus 3 minus 43. What? 43 times 10 to the power minus 6 minus A, 0.37 divided by 0.6 into 10 to the power minus 3. This will be Newton per meter square. So we have to calculate the ratio. So I have to calculate Pi by PV. Renuka do it, and others also. Hello. It seems my internet connection actually went off. So is my screen visible? Now you can see my screen.
Yes, sir.
Yeah. So I just actually my internet went off. So so this is the thing. So please do the calculation and tell me what is the ratio. There will be one square here.
Option C, sir.
Option C 0.95.
Yeah.
Let me check. So this is v square, so 0.6 square. So let me check. So my value is coming out to be for this. This is 3.447 times 10 to the power 6. Now if you take the ratio, this is 4.155, this is 3.447. Let me take it. 4.155 divided by 3 so option C is not correct for sure. 447, so this is coming out to be 1.205.
0.20 D option. Sir, I think I have got it PV equal to 4.4779, sir. I will check it, sir.
4.4779. Probably you didn't this square term you didn't calculate. This thing you didn't do.
Once again, I will check it, sir.
So you didn't get this a by
Yeah,
v
yeah,
square.
yeah, yeah, yeah.
That's why.
Yes, sir. Yes, sir.
That's right. Anyway, so you will get it. So yeah. Okay. So the last problem. for today. This says the dimension of B in van der Waals gas equation is similar to that of pressure, temperature, volume, or option D, B is dimensionless constant. Please tell me. I'm writing the van der Waals equation, okay? So what is the dimension of B? Sorry, dimension of B. Please, this is very simple, right? Please tell me. This is very simple. So to add
Volume, sir.
volume, right? So to add or to subtract from some quantity, you need to have same dimension, right? So since there is V minus B, so they need to be of same dimension. So that's why, as Renuka said correctly, dimension of will be same as volume. Okay. Okay. So thank you. I will be here. So this is the end of this today's session. So next week probably we'll not meet on Monday because we have a PMRF annual PMRF symposium at IIT Indoor. So I have to attend it. So you guys will know by mail then when we will do this session, the next week session. I will actually this NPTEL people will let you know. They will inform you that this session, but that will be also be of 2 hours. So till then, uh, take care uh, and good night.